115 different chemical elements are known to us at present. These elements combine to form a large number of compounds. On the basis of their chemical properties, all the compounds can be classified into 3 groups: 1 acids, 2 bases, and 3 salts. In this chapter, we will study all the 3 types of compounds, acids, bases and salts, in detail. In order to know whether a substance is an acid or a base, we should first know the meaning of the term acid-base indicator, or just indicator. An indicator is a dye that changes color when it is put into an acid or a base. An indicator gives different colors in acid and base. Thus, an indicator tells us whether the substance we are testing is an acid or a base by change in its color. In other words, an indicator tells us whether the substance we are testing is acidic or basic by change in its color. The 3 most common indicators to test for acids and bases are litmus, methyl orange and phenolphthalein. The most common indicator used for testing acids and bases in the laboratory is litmus. Litmus can be used in the form of litmus solution or in the form of litmus paper. It is of 2 types, blue litmus and red litmus. An acid turns blue litmus to red. A base, or alkali, turns red litmus to blue. Litmus is a natural indicator, whose neutral color is purple. It is made into blue litmus and red litmus for the sake of convenience in detecting color change when an acid or base is added to it. But methyl orange and phenolphthalein are synthetic indicators. The neutral color of methyl orange is orange. Methyl orange indicator gives red color in acid solution. Methyl orange indicator gives yellow color in basic solution. The neutral color of phenolphthalein is colorless. Phenolphthalein indicator is colorless in acid solution. Phenolphthalein indicator gives pink color in basic solution. Olfactory indicators. The term olfactory means relating to the sense of smell. Those substances whose smell or odor changes in acidic or basic solutions are called olfactory indicators. An olfactory indicator usually works on the principle that when an acid or base is added to it, then its characteristic smell cannot be detected. Onion and vanilla extract are olfactory indicators. Onion has a characteristic smell. When a basic solution like sodium hydroxide solution is added to a cloth strip treated with onions, or onion extract, then the onion smell cannot be detected. An acidic solution like hydrochloric acid, however, does not destroy the smell of onions. This can be used as a test for acids and bases. Vanilla extract has a characteristic pleasant smell. If a basic solution like sodium hydroxide solution is added to vanilla extract, then we cannot detect the characteristic smell of vanilla extract. An acidic solution like hydrochloric acid, however, does not destroy the smell of vanilla extract. This can be used as a test for acids and bases. How do acids and bases react with metals? When an acid reacts with a metal, then a salt and hydrogen gas are formed. That is, metal plus acid give rise to salt plus hydrogen gas. For example, when dilute sulfuric acid reacts with zinc metal, then zinc sulfate and hydrogen gas are formed. In this reaction, zinc metal displaces hydrogen from sulfuric acid. And this hydrogen is evolved as hydrogen gas. Most of the acids react with metals to form salts and evolve hydrogen gas. This shows that hydrogen is common to all acids. The reaction of dilute sulfuric acid with zinc metal to show the formation of hydrogen gas can be carried out as follows. Take a few pieces of zinc granules in a boiling tube and add about 5 ml of dilute sulfuric acid to it. We will observe the formation of gas bubbles on the surface of zinc granules. Past the gas being formed through the soap solution taken in a trough, by means of a glass delivery tube. Gas-filled bubbles are formed in the soap solution which rise into the air. Bring a burning candle near a gas-filled soap bubble. The gas present in soap bubble burns with a pop sound, making a little explosion. Only hydrogen gas burns making a pop sound. This shows that hydrogen gas is evolved in the reaction of dilute sulfuric acid with zinc metal, taken in the form of zinc granules. When a base reacts with a metal, then a metal salt and hydrogen gas are formed. For example, place a few pieces of granulated zinc metal in a test tube. Add 2 ml of sodium hydroxide solution and warm the contents of the test tube. Repeat the rest of the steps. When sodium hydroxide solution is heated with zinc, then sodium zincate and hydrogen gas are formed. In the sodium zincate salt formed by the reaction between sodium hydroxide and zinc metal, the zinc metal is present as a part of the negative ion, zincate ion. It is very important to note that all the metals do not react with bases to form salts and hydrogen gas. The reaction between dilute hydrochloric acid and sodium carbonate can be performed as follows. Take a boiling tube and put about 0.5 g of sodium carbonate in it. Add about 2 ml of dilute hydrochloric acid in the boiling tube, through a thistle funnel. We will observe that brisk effervescence of a gas is produced. Pass the gas through lime water. The lime water turns milky, showing that it is carbon dioxide gas. Keep on passing carbon dioxide gas through milky lime water for some more time. The lime water becomes clear again. This shows that the white precipitate of calcium carbonate dissolves on passing excess of carbon dioxide gas. We can repeat this experiment by using sodium hydrogen carbonate in place of sodium carbonate. Again we will get carbon dioxide gas which will turn lime water milky. On passing excess of carbon dioxide, the milky lime water will become clear again. When dilute hydrochloric acid reacts with sodium carbonate, then sodium chloride, carbon dioxide and water are formed. When dilute hydrochloric acid reacts with sodium hydrogen carbonate, then sodium chloride, carbon dioxide and water are formed. Thus, acids react with carbonates and hydrogen carbonates to evolve carbon dioxide gas. This carbon dioxide gas reacts with lime water, calcium hydroxide solution, as follows. When carbon dioxide gas is passed through lime water, the lime water turns milky due to the formation of a white precipitate of calcium carbonate. If excess of carbon dioxide gas is passed through lime water, then the white precipitate formed first dissolves due to the formation of a soluble salt calcium hydrogen carbonate, and the solution becomes clear again. How do acids and bases react with each other? When an acid reacts with a base, then a salt and water are formed. That is, acid plus base give rise to salt plus water. Actually, when an acid is treated with a base, the base neutralizes the acid and destroys its acidity. Since an acid and a base neutralize each other's effect, so the reaction between an acid and a base to form salt and water is called a neutralization reaction. For example, when hydrochloric acid reacts with sodium hydroxide solution, then a neutralization reaction takes place to form sodium chloride and water. It nullify each other to form sodium chloride salt, which is neither acidic nor basic. It is neutral. Reaction of metallic oxides with acids. Acids react with metal oxides to form salt and water. Metal oxide plus acid give rise to salt plus water. Copper, second, Oxide is a metal oxide. Dilute hydrochloric acid reacts with copper, second, oxide to form copper, second, chloride and water. We can carry out the reaction between copper, 2, oxide and dilute hydrochloric acid as follows. I. Take a small amount of copper, 2, oxide in a beaker. It is black in color. 2. Add dilute hydrochloric acid slowly while stirring with a glass rod. 3. We will find that copper, 2, oxide has dissolved in dilute hydrochloric acid to form a blue-green solution. 4. The blue-green color of the solution is due to the formation of copper, 2, chloride salt. The reaction between acids and metal oxides to form salt and water is similar to the neutralization reaction between an acid and a base to form salt and water. Thus, the reaction between acids and metal oxides is a kind of neutralization reaction. It shows the basic nature of metal oxides. Reaction of a non-metallic oxide with bases react with non-metal oxides to form salt and water. Non-metal oxide plus base give rise to salt plus water. Now, calcium hydroxide is a base and carbon dioxide is a non-metal oxide. So, calcium hydroxide solution reacts with carbon dioxide to produce calcium carbonate and water. The reactions of non-metal oxides with bases to form salt and water show that non-metal oxides are acidic in nature. What do all acids and all bases have in common? Take solutions of hydrochloric acid, sulfuric acid, glucose and alcohol. All these are hydrogen-containing compounds. 2. Fix 2 iron nails on a rubber cork and place the cork in a beaker. 3. Connect the nails to the 2 terminals of a 6-volt battery through a switch and a bulb. 4. Pour some dilute hydrochloric acid solution, HCl solution, in the beaker and switch on the current. The bulb starts glowing. This shows that hydrochloric acid solution taken in the beaker conducts electricity. Let us now take glucose solution in the beaker and switch on the current. The bulb does not glow in this case. This shows that glucose solution does not conduct electricity. If we repeat this experiment by taking alcohol solution in the beaker, the bulb does not glow again. This shows that alcohol solution also does not conduct electricity. The aqueous solution of an acid conducts electricity due to the presence of charged particles called ions in it. For example, when hydrochloric acid is dissolved in water, then its solution contains hydrogen ions and chloride ions. These ions can carry electric current. So, due to the presence of hydrogen ions and chloride ions, a solution of hydrochloric acid conducts electricity. And this makes the bulb glow. On the other hand, the hydrogen-containing compounds like glucose and alcohol do not produce hydrogen ions or some other ions in solution. So, due to the absence of ions, glucose solution and alcohol solution do not conduct electricity. Distilled water does not conduct electricity because it does not contain any ionic compound, like acids, bases or salts, dissolved in it. What happens to an acid or a base in a water solution? We will now describe an experiment to show that acids do not show acidic behavior without water. We will take the example of hydrogen chloride gas for this purpose. Dry hydrogen chloride gas, dry HCl gas, does not show acidic behavior, but when some water is present, then its acidic behavior can be observed. Take about 1 gram solid sodium chloride, NaCl, in a clean and dry boiling tube and add some concentrated sulfuric acid to it very carefully. Fit a rubber cork with a small glass delivery tube in the mouth of the boiling tube. Concentrated sulfuric acid reacts with sodium chloride to form hydrogen chloride gas. The hydrogen chloride gas starts coming out of the open end of the glass tube. hold a dry, blue litmus paper in hydrogen chloride gas. There is no change in the color of dry, blue litmus paper. This shows that hydrogen chloride gas, HCl gas, does not behave as an acid in the absence of water. We now hold a moist or wet blue litmus paper in hydrogen chloride gas. We will see that the moist blue litmus paper turns red. This shows that hydrogen chloride gas, HCl gas, shows acidic behavior in the presence of water. Dry HCl gas does not contain any hydrogen ions in it, so it does not show acidic behavior. In fact, dry HCl gas does not change the color of dry blue litmus paper because it has no hydrogen ions in it. However, when HCl gas dissolves in water, it forms hydrogen ions and hence shows acidic behavior. Actually, hydrogen chloride gas, HCl, G, first dissolves in water to form hydrochloric acid solution, which then produces hydrogen and calcium ions. The separation of hydrogen ions from HCl molecules cannot occur in the absence of water. The separation of H+ ions from HCl molecules can occur only in the presence of water. That is why HCl gas shows acidic behavior only in the presence of water. The HCl gas turns wet blue litmus paper red because it dissolves in the water present in wet litmus paper to form hydrogen ions, which can turn blue litmus paper to red. Please note that the above reaction of dissolving HCl gas in water can also be written in another way as follows, in which hydrogen ions are written in the form of hydronium ions. When a base is dissolved in water, it always produces hydroxide ions, or ions. Thus, a base is a substance which dissolves in water to produce hydroxide ions, or ions, in solution. For example, sodium hydroxide is a base because it dissolves in water to produce hydroxide ions, along with sodium ions. A sodium hydroxide solution shows basic behavior due to the presence of hydroxide ions in it. Similarly, potassium hydroxide is a base which dissolves in water to give hydroxide ions, along with potassium ions. From the above discussion we conclude that a common property of all the bases, or alkalis, is that they all produce hydroxide ions, or ions, when dissolved in water. Now H, KOH, Mg, O2, Ca2, and NH4O are all bases, or alkalis, because they dissolve in water to produce hydroxide ions. How strong are acid or base solutions? In 1909 Sorensen devised a scale, known as pH scale, on which the strength of acid solutions as well as basic solutions could be represented by making use of the hydrogen ion concentrations in them. Sorensen linked the hydrogen ion concentrations of acid and base solutions to the simple numbers 0 to 14 on his pH scale. The pH of a solution is inversely proportional to the concentration of hydrogen ions in it. That is, a solution having a high concentration of hydrogen ions has a low pH value. On the other hand, a solution having low concentration of hydrogen ions has a high pH value. In the term pH, letter P stands for a German word, potens, which means power, and letter H stands for hydrogen ion concentration. Neutral substances have a pH of exactly 7. Pure water is a neutral substance, it is neither acidic nor basic. So, the pH of pure water is 7. A sugar solution and sodium chloride solution are also neutral, each having a pH of 7. So, whenever the pH of a solution is 7, it will be a neutral substance. Acids, or acidic solutions, have a pH of less than 7. Whenever a solution has a pH of less than 7, it will be an acidic solution. For example, A solution having a pH of 4 will be acidic in nature. A solution of pH 1 is much more acidic than another solution of pH 4. In other words, a solution of pH 1 will be a much more stronger acid than another acid having pH 4. All the solutions having pH less than 7 are acidic in nature and hence they turn blue litmus to red. They also turn methyl orange indicator red. Bases, or basic solutions, have a pH of more than 7. Whenever a solution has a pH of more than 7, it will be a basic solution or alkaline solution, or it will be a base or an alkali. For example, a solution having a pH of 11 will be basic in nature. The more basic a solution is, the higher will be its pH. A solution of pH 14 will be much more basic than another solution of pH 10. In other words, a solution of pH 14 will be a much more stronger base than another solution of pH 10. All the substances having pH more than 7 are basic in nature, or alkaline in nature, and hence they turn red litmus to blue. They also turn phenolphthalein indicator pink. An acid which is completely ionized in water and thus produces a large amount of hydrogen ions is called a Stroin acid. For example, hydrochloric acid is completely ionized in water, so it is a Stroin acid. The single arrow pointing towards right in the above equation indicates that hydrochloric acid is completely ionized to form ions. Sulfuric acid and nitric acid are also Stroin acids because they are fully ionized in water to produce a large amount of hydrogen ions. Stroin acids react very rapidly with other substances, such as metals, metal carbonates and metal hydrogen carbonates, etc. Stroin acids also have a high electrical conductivity because of the high concentration of hydrogen ions in their solution. An acid which is partially ionized in water and thus produces a small amount of hydrogen ions is called a weak acid. For example, acetic acid is partially ionized in water to produce only a small amount of hydrogen ions, so it is a weak acid. The double arrow pointing towards right as well as left in the above equation tells us that acetic acid does not ionize fully to form hydrogen ions. Carbonic acid and sulfurous acid are also weak acids because they ionize only partially in water to form a small amount of hydrogen ions. Due to a small amount of hydrogen ions present in their solutions, weak acids react quite slowly with other substances, such as metals, metal carbonates and metal hydrogen carbonates, etc. Weak acids have low electrical conductivity because of the low concentration of hydrogen ions in them. A base which completely ionizes in water and thus produces a large amount of hydroxide ions, or ions, is called a Stroin base, or a Stroin alkali. Sodium hydroxide, NaOH, and potassium hydroxide, KOH, are Stroin bases, or Stroin alkalis. This is because they completely ionize on dissolving in water to produce a large amount of hydroxide ions. A base which is partially ionized in water and thus produces a small amount of hydroxide ions is called a weak base, or weak alkali. Ammonium hydroxide, calcium hydroxide and magnesium hydroxide are weak bases, or weak alkalis. This is because they ionize only partially on dissolving in water and produce a small amount of hydroxide ions. Family of salts. The salts having the same positive ions, or same negative ions, are said to belong to a family of salts. For example, sodium chloride and sodium sulfate belong to the same family of salts called sodium salts, because they both contain the same positively charged ions, sodium ions. Similarly, sodium chloride and potassium chloride belong to the same family of salts called chloride salts, because they both contain the same negatively charged ions, chloride ions. We can have as many families of salts as the positively charged ions and negatively charged ions, which make up the salts. Some of the important families of salts are sodium salts, calcium salts, magnesium salts, zinc salts, potassium salts, aluminium salts, copper salts, ammonium salts, chloride salts, sulfate salts, nitrate salts, carbonate salts and acetate salts. The common salt is a white powder which is used in preparing food, especially vegetables and pulses, etc. The chemical name of common salt is sodium chloride, NaCl. Common salt, or sodium chloride, is a neutral salt. Common salt, sodium chloride, occurs naturally in seawater and as rock salt. Common salt occurs in dissolved form in seawater. On the other hand, common salt occurs in solid form as rock salt. Common salt from seawater. Seawater contains many dissolved salts in it. The major salt present in seawater is common salt, or sodium chloride. Common salt is obtained from seawater by the process of evaporation. Common salt from underground deposits. Underground deposits of common salt are found in many parts of the world. The large crystals of common salt found in underground deposits are called rock salt. Rock salt is usually brown due to the presence of impurities in it. Rock salt is mined from the underground deposits just like coal. Sodium hydroxide. Sodium hydroxide is commonly known as caustic soda. The chemical formula of sodium hydroxide is NaOH. Sodium hydroxide is a very important basic chemical which is used as a starting material for making many other chemicals. Sodium hydroxide is produced by the electrolysis of a concentrated aqueous solution of sodium chloride, which is called brine. When electricity is passed through a concentrated solution of sodium chloride, called brine, it decomposes to form sodium hydroxide, chlorine and hydrogen. During electrolysis, chlorine gas is produced at the anode, positive electrode, and hydrogen gas is produced at the cathode, negative electrode. Sodium hydroxide solution is formed near the cathode. All the products of electrolysis of sodium chloride solution, chlorine, hydrogen and sodium hydroxide, are collected and stored separately. The process of electrolysis of sodium chloride solution is called chloralkali process because of the products formed, chlor for chlorine and alkali for sodium hydroxide. The three very useful products obtained by the electrolysis of sodium chloride solution called brine, or chloralkali process, are sodium hydroxide, chlorine and hydrogen. Bleaching powder is calcium oxychloride. Bleaching powder is prepared by passing chlorine gas over dry slaked lime. Bleaching powder is a white powder which gives a strong smell of chlorine. Bleaching powder is soluble in cold water. The small insoluble portion always left behind is the lime present in it. Bleaching powder reacts with dilute acids to produce chlorine. The chlorine produced by the action of a dilute acid on bleaching powder acts as a bleaching agent. Thus, the real bleaching agent present in bleaching powder is chlorine. Uses of bleaching powder. Bleaching powder is used for bleaching cotton and linen in textile industry and for bleaching wood pulp in paper industry. It is also used for bleaching washed clothes in laundry. Bleaching powder is used for disinfecting drinking water supply. That is, for making drinking water free from germs. Bleaching powder is used for the manufacture of chloroform. Bleaching powder is used for making wool unshrinkable. Bleaching powder is used as an oxidizing agent in many chemical industries. The chemical name of baking soda is sodium hydrogen carbonate. The formula of baking soda is Na.H.CO3. It is also called sodium bicarbonate. Baking soda is sometimes added for faster cooking of food. Sodium hydrogen carbonate is produced on a large scale by reacting a cold and concentrated solution of sodium chloride, called brine, with ammonia and carbon dioxide. Sodium hydrogen carbonate consists of white crystals which are sparingly soluble in water. Sodium hydrogen carbonate is a mild, non-corrosive base. The solution of sodium hydrogen carbonate in water is mildly alkaline. When solid sodium hydrogen carbonate, or its solution, is heated, then it decomposes to give sodium carbonate with the evolution of carbon dioxide gas. Uses of sodium hydrogen carbonate, or baking soda. Sodium hydrogen carbonate is used as an antacid in medicine to remove acidity of the stomach. Being alkaline, sodium hydrogen carbonate neutralizes the excess acid present in the stomach and relieves indigestion. Sodium hydrogen carbonate, or baking soda, is used in making baking powder, used in making cakes, bread, etc. Baking powder is a mixture of baking soda and a mild, edible acid such as tartaric acid. When baking powder mixes with water, present in dough made for baking cake or bread, then sodium hydrogen carbonate reacts with tartaric acid to evolve carbon dioxide gas. Sodium hydrogen carbonate is used in fire extinguishers. Washing soda. Washing soda is sodium carbonate containing 10 molecules of water of crystallization. That is, washing soda is sodium carbonate decahydrate. The formula of washing soda is Na2CO3.10H2O. Sodium carbonate which does not contain any water of crystallization is called anhydrous sodium carbonate. Anhydrous sodium carbonate is commonly known as soda ash. Washing soda is an important chemical obtained from sodium chloride. Washing soda is a transparent crystalline solid. Washing soda is one of the few metal carbonates which are soluble in water. The solution of washing soda in water is alkaline, which turns red litmus to blue. Washing soda has detergent properties because it can remove dirt and grease from dirty clothes, etc. Washing soda is produced from sodium chloride, or common salt, in the following 3 steps. First, a cold and concentrated solution of sodium chloride, called brine, is reacted with ammonia and carbon dioxide to obtain sodium hydrogen carbonate. Second, sodium hydrogen carbonate is separated by filtration, dried and heated. On heating, sodium hydrogen carbonate decomposes to form sodium carbonate. Finally, anhydrous sodium carbonate, soda ash, is dissolved in water and recrystallized to get washing soda crystals containing 10 molecules of water of crystallization. Uses of sodium carbonate, or washing soda. Sodium carbonate, or washing soda, is used as a cleansing agent for domestic purposes like washing clothes. In fact, sodium carbonate is a component of many dry soap powders. Sodium carbonate is used for removing permanent hardness of water. Sodium carbonate is used in the manufacture of glass, soap and paper. Sodium carbonate is used in the manufacture of sodium compounds such as borax. Plaster of Paris. Plaster of Paris is calcium sulfate hemihydrate, calcium sulfate half hydrate. The formula of plaster of Paris is CaSO4.half.H2O. The name plaster of Paris came from the fact that it was first of all made by heating gypsum, which was mainly found in Paris. Plaster of Paris is prepared from gypsum. Gypsum is calcium sulfate dihydrate. That is, gypsum is calcium sulfate containing 2 molecules of water of crystallization. Plaster of Paris is prepared by heating gypsum to a temperature of 100 degrees Celsius in a kiln. When gypsum is heated to a temperature of 100 degrees Celsius, it loses 3/4 of its water of crystallization and forms plaster of Paris. In the preparation of plaster of Paris, heating of gypsum should be controlled carefully. The temperature during the heating of gypsum should not be allowed to go above 100 degrees Celsius. This is because if gypsum is heated above 100 degrees Celsius, then all its water of crystallization is eliminated and anhydrous calcium sulfate called dead burnt plaster is formed. The anhydrous calcium sulfate does not set like plaster of Paris on adding water. Uses of plaster of Paris. Plaster of Paris is used in hospitals for setting fractured bones in the right position to ensure correct healing. It keeps the fractured bone straight. Plaster of Paris is used in making toys, decorative materials, cheap ornaments, cosmetics, blackboard chalk and casts for statues. Plaster of Paris is used as a fireproofing material. Plaster of Paris is used in chemistry laboratories for sealing air gaps in apparatus where airtight arrangement is required. Plaster of Paris is used for making surfaces, like the walls of a house, smooth before painting them, and for making ornamental designs on the ceilings of houses and other buildings.